Hello, and welcome to our presentation on detecting and classifying aquatic insects with computer vision.
Now we're going to briefly look at our problem. We have multiple of these sticky tabs, and we want to basically get the insect distribution on them. So we want to, the first step in our process is to identify objects and assess whether that object is an insect or dirt or bits or stuff like that, and then classify it into the proper taxonomical order.
So we faced a problem with the imbalanced data set where we had some orders of the insects be the dominants. So we tried to solve that with augmentation, and you can see the results of showing more uh, of the rarer classes on that light augmentation. And after heavy augmentations, you can see that other classes have their own good share that could help the model detect them well. So we start our pipeline with the YOLO detection that takes the whole image and detect each insect inside that image. We faced some challenges that was a problem with detecting, especially the tiny relay insects, which we solved by using a specific architecture that kept the future of each small insects. Also, we faced a problem of the high resolution images causing slow detections, which we solved by using SAHI.
So, Sahi is essentially a setting that can be used in the Yellow 11 model. And what it does is instead of taking in the whole image, it uses a moving window to go across the image and it zooms into that window, which is what allows it to get some of these smaller insects within the super dense areas that the normal Yellow 11 model is not able to achieve. So by using Sahi, we can potentially get a more accurate detection of all the insects in a sticky trap.
Let's talk about the second stage of our pipeline, that is classification. We finalized on using the resonant model for classification, and makes use of convolutional neural networks and skip connections or residuals. Let's talk about the results. The best accuracy we had was 91% on the testing set. Our initial model did well for all classes except for the other class, which may consist of any insect that doesn't fall into these five limited categories of caddisfly, dipteran, stonefly, terrestrial, and mayfly. As I highlighted before, we also had a problem of the classes being imbalanced, and we tried to address this in various ways. The ways that worked the best was augmentation. We also tried other ways like using class weights and focal loss functions. But now, for the other class, we had a particular difficulty putting items into it. So we handled this by using label smoothing, which basically aims to reduce overconfidence of the class. And we also use confidence thresholding that puts the less confident predictions into the into the other class.
Yeah, so finally we've read on the user interface, which is as follows, which you can see. So what we wanted was to create a website where like someone who works at the Bernard Tab or at Hubbard Brook was able to engage with our model and like upload their images independent of having the ability to know what the R code really does. So it's sort of a black box where as you can see like on the UI, there's a home and about page, and then as you log in you get an account page, and then you'll have a page where you'll be able to upload an image, and then there'll be a results page which will give you a summary of all the insects and their orders, in addition to a picture of a sticky trap which would have the bounding boxes marked on them as well. And then all this data can then be downloaded uh, as a CSV or a JSON file, which can then be exported or which can then be used to make changes to low confidence insects, which will be classified by the model as others. Thank you. This was our video for our presentation for our project. Thank you.